Okay, so let's see. Um, okay, so here's a matrix. So what is the column rank of this matrix?
Two, because the bottom one is 0.
Yes.
So just need the first one and the second one.
So the row rank, what's the row rank?
Well, there's 2.
Yeah, there's 2 non-zero rows. It's an echelon. So the things you verify are, okay, it's an echelon form. There's 2 non-zero rows. So the rank of the matrix equals 2, and so therefore the column rank equals 2, even though there's 3 columns. Okay. Well, we could do more problems like this, or should we do, let me see, let me do maybe one more, and then we can go and work on assignments if that's okay. The problems. Okay, so let's see. Let's say we have a space A equals of X, Y, Z, X, Y, Z, W, such that X plus Y equals 0 and Z plus W equals 0. Probably done this before. But, so, and the question is, find a basis. So what do I do? Well, this is a linear system over here that determines what these numbers could be. And it's already in some sense, if I wrote it out, it would be X plus Y, Z plus W equals 0. So it's already in echelon form. If just to make it clear, this would be the augmented matrix for the linear system. It's so sparse that it sort of fools you because it looks like that. Okay, well, so you can see that X and Z are leading and Y and W are free. So that's a little bit overkill, but we can just solve this. We want to get rid of the leading variables here. So we'll say X equals minus Y and Z equals minus W, and these are the free, and these are therefore the leading. So then I have A equals minus Y, minus W, such that Y and W are any real numbers, because that's what's left over from Y and W being free. There's no constraints because we've satisfied the linear system by removing the leading variables. Now, if we're trying to get a basis, we're trying to represent the space A as a span. So we can write this as, by factoring out the constant, so we can say this is Y times, pretending the W is 0, we'll get minus 1, 1, 0, 0, right? Wait, what am I doing? What, you see, yes, Y and W, okay, so, yes, okay, plus W. Okay. Sorry, I'm thinking of something else at the moment. Okay, minus 1, Y and W, numbers of R. So you can see that this is, if I multiply the Y in here, I have minus YY, I'll have minus WW. If I add them together, I get this. So this is just the vector arithmetic, but I've written as a span, right? So what we've done is we've written as A equals the span of minus 1, 1, 0, 0, and 0, 0, minus 1, such that what? Oh, there's no such that. This is just the span. That's part of the definition of span. So we have the span of this set. Well, so if those two vectors are linearly independent, then this span is the basis. And in fact, it is, because you can see that if A times the first vector plus B times the second equals 0, the top ones are going to give you, the top two equations are going to give you A is 0, the bottom two give you B is 0. So the vectors are linearly independent by the linear independence test. And so the basis for basis B equals minus 1, 0, 0, and 0, 0, minus 1, 1. Okay, let's do one last question for you. Let's say that I have let's say that I have a 4x4 invertible matrix. What is the column rank of the matrix?
I forgot what does invertible mean again?
It means it has an inverse. So that, like, if the matrix here is, say, n, then there's an n inverse such that n equals the identity element.
Oh, I can't remember that. Okay.
So what's the column rank of the matrix?
I mean, I think guess immediately, I guess that's like 4, just because it's like 4x4. But
Yes, and that would be good, because, well, you sort of, it's like absence of any other information. How else are you going to answer the problem, right? I mean,
yeah.
okay, well, but the question is, so why? Why would you could then ask, well, why would the rank be 4? These are connected. Here's the idea. Well, if a map that's if let's say that we have n here that's invertible, right? Well, what we form is we find the inverse, right? By doing this, by putting a 4x4 identity here, say if we have a 4x4 matrix, and then we use row operations to achieve what result? If it's invertible, what's the final result of doing the Gauss's method? When you use the giant augmented matrix, what are you looking for? you want to see that this one becomes the identity, then this will be this matrix over here will be the inverse. Okay? So Gauss's method for an invertible matrix takes n and reduces it to this. So this is the reduced row echelon form. So how many free variables does this have? This side is going to look like this, right? One. This is an echelon form. Echelon form version of n, right? So what is its rank? What is its row rank? Well, row rank is the dimension of row space. So if I take these rows in echelon form, these rows span the same space as the rows of n, and in echelon form, the rows are linearly independent. So 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, these rows form a basis of row space. So what's the dimension of row space?
4.
4. It's got to be 4. So that means the rank is 4. So the reason that if you have a 4x4 invertible matrix, that means that its reduced to echelon form is the identity matrix, which means that its rank is 4. So if you have an n by n invertible matrix, the only way you can get it invertible is if it's maximal rank, because the rank is the number of non-zero rows for the matrix in echelon form. Okay, if you had, maybe we should do this again. If you had a 5 by 5 matrix and say Q, and the rank of Q equals 2, how many free variables? How many free variables would a linear system with Q in, if this is Q, we'd have X, Y, Z, W, U equals 1, 2, 3, 4, 5. How many free variables does this linear system have?
I'd say 3.
Yes, that's correct. Because if it's a 5 by 5 matrix and you have the rank is 2, that means if you put it in echelon form, it's going to have 2 non-zero rows, right? That means there's going to be 2 leading variables, because a leading variable for each row. But you've got 5 variables, because it's a 5 by 5 matrix, so there's got to be 5 minus 2 or 3. 5 minus 2 equals 3 free variables. Okay. So these are all sort of like, you've got a lot of words, a lot of concepts, and they're all connected. And so you can by not sort of realizing what the rank is, or the dimension of the basis, if you sort of like, you've got many words but only a few actual things, and they're all connected. So the rank is connected to the free variables and the size of the matrix, right? So there's information that you can deduce from other information. Okay. Why don't we now